That's more like it. All right, guys, sorry about that. I accidentally joined the wrong Zoom meeting. I start talking out of the car. I go, where the fuck is everybody? So welcome back to Calc 2. Today we are going to talk about trigonometric substitutions in integrals. So over the last few days, we've discussed how to solve integrals of trig functions, products of powers of sine and cosine, products of powers of secant and tangent. And we primed you a little bit for the concepts of Trig Sub on Wednesday. Today, we're going to develop those in full. I did want to apologize. I know our classes have been running slightly over time lately, and it was brought to my attention. I don't know if it was somebody in this class or somebody elsewhere, that can put a strain on y'all. I don't want to do that. So I am going to stick more closely to the official scheduled time of the class from here on out. Of course, it is unfair to you guys to take up more of your time than you bargained away in this class. So today, Trig Sub, and I promise we will end on time. Let me go ahead and fire up the document camera. There we go. We can share the screen and begin. All right. So we got to start as we always do. This is MAC2312. Section number is 004, which is Calc 2, and the date today is the 28th of January, 2022. This pen is dying. It's good. These are the bad ones. Oh, this one's hanging in there. All right. Focus. Focus. All right. So today, we're going to do section 7.3, which is Trig Sub. And just a little word about the exam. The exam is drawing nearer and nearer. On Monday of next week, we're going to talk about partial fractions, section 7.4. And 7.4 is the last section that has any new material for the test. Between 7.4 and the test, we will also cover section 7.5, but 7.5 doesn't actually have any new material. It's called strategies for integration. So let me show you really quickly. So your test will cover section 5.5 on substitution, 6.1, 6.2 on volumes, 6.1 on areas between curves, 6.2 and 6.3 on volumes, 6.4 on work, 6.5 on average value, and then 7.1, 7.2, 7.3, 7.4, which is what we're going to do Monday, and then 7.5, which is not a section that introduces a new technique or a new application or anything like that. There really is nothing new in 7.5, besides a little discussion on, if I give you an integral, how do you figure out which thing to try? Should you try integration by parts or trig sub? Should you try u sub, right? So this section 7.5 is sort of a review section where you combine all the methods from the previous 4 sections in chapter 7. And your study guide will come primarily from section 7.5. Test is not next Monday. No, so next Monday, I will finish the material for the test. I will finish all of the material that's going to be on the test on Monday, which means the test itself will be the following Monday, maybe that Friday. I'll have to think about it, but probably the following Monday. I like to give you guys a week with the study guide. So next Monday, I will lecture on 7.4, which is partial fractions, and I will publish your study guide, which will come from section 7.5. We will talk a little bit about 7.5 next Wednesday, and then your test will probably be the following Monday, which I believe is the 7th. Let's see, February. Yeah, looks like your test will be on the 7th. Now I reserve the right to change that a little bit depending on how things go, if we need more time or less time on one of those sections, but probably the 7th. All right. Let's get into the good stuff today. I don't want to waste any time. We know how to integrate trig functions now. And we saw at the end of class last time that the square root of 1 minus x squared is a hard function to integrate. What I'm going to begin with here is something I call the Trig Sub Bible. I'm not religious. If you are religious, please, I don't mean any offense by calling it that. It's just the terminology that sticks in my head best. And this is broken, it's a table that's broken up into two columns. If your integral contains something that I put in the left column, you're going to make the substitution that I put in the right column. All of the things over here are going to be square roots because Trig Sub is meant to help us handle gnarly square roots. There are a lot of integrals that are hard just because you've got some shit under a square root and you can't split up the square root. So if your integral contains something of the form a squared minus x squared, where a is a constant, then you're going to make the substitution x equals a times the sine of theta. And the integral we saw at the end of class on Wednesday falls into this category, right? 1 minus x squared. If your integral contains something like the square root of a squared plus x squared, a sum of a constant and your variable squared, you're going to make the substitution x equals a times the tangent of theta. And if your integral contains a square root of something like x squared minus a squared, where the variable comes first, they're being subtracted, then you're going to substitute something like x equals a times the secant of theta. So this is your Trig Sub Bible or guideline, whatever. If you see some shit that looks like this, you're probably going to do a substitution like this. The big idea is that the square root of something like, I don't know, a squared plus or minus x squared, this is not the same as a plus or minus x. Square roots do not split up over addition or subtraction. Square roots do not distribute over addition or subtraction. Which means if you have one of those things showing up in your integral, it can be quite hard to figure out how to make them nice. The word here is make substitution. So the first thing I need you to make sure is baked all the way in your brain is the statement next to big idea down here, right? We cannot do this. When you see square roots like these, you cannot do stuff like this. So then what do? Well, you do this, right? You perform the substitution that's indicated by the Trig Sub Bible. You can check that these statements aren't true, right? Like if you just plug in some numbers here, like 1 and 2, the square root of 1 squared plus 2 squared would be the square root of 5, which is an irrational number. That is not the same as 1 plus 2, which would be 3, right? 5 is not the square root of 3. 3 is not the square root of 5. So this shit don't work. This shit I claim will work. And the reason why if I make x equal to, let me say a times the tangent of theta, I'll do that one. Then the square root of a squared plus x squared will be the square root of a squared plus a squared tan squared theta, right? Because x is a times the tangent of theta, x squared is a squared times tangent squared theta. You can factor out the a squared inside the square root. So you have a squared times parentheses 1 plus tan squared theta. And then you can use a trig identity. 1 plus tangent squared theta is secant squared theta. So this is a squared times secant squared theta. And you cannot split up a square root over addition or subtraction, but you can split them up over multiplication and division. So now I can take the square root of a squared, which is a, and the square root of secant squared, which is secant. So the miracle is by making this substitution, you're able to get rid of the square root. And square roots make integrals hard, so we're happy to get rid of them. I would much rather integrate the secant of theta than some gnarly shit under a square root. Now, of course, there's going to be other stuff going on in these integrals. We will have more work to do than just this. There will be a trig integral you need to do at the end. And then depending on whether you're doing a definite integral or an indefinite integral, you'll either have to change your bounds as you go through the substitution, or you'll have to go back to your original variable if you're looking at an indefinite integral. But the miracle of this technique, the miracle of these substitutions, is that they each get rid of the associated square root. So if you substitute x equals a sine theta in a square root like this, the result will be a cos theta. The square root will go away. That's the nice thing here. And the same is true for the other ones. These substitutions kill these square roots. Okay. Now, I promised to do the integral of the square root of 1 minus x squared, and we will do that, but I'd like to start out with something that's a little gentler because that one is a somewhat complicated problem. So let me just grab a slightly more gentle example from your textbook. This one is somewhat fun. Sure, let's do that. All right, I'll hold here for a second. Anybody need time to write still? Okay. So gentle example first. Let's evaluate the integral of the square root of 9 minus x squared. Was it just x or x squared? X squared. Dx. So I do have one of these gnarly square roots in my problem, which means I'm going to do some trig sub. You need to match this up with the trig sub Bible and see which substitution you're going to make and what is the value of a. So this to me looks like a squared minus x squared, right? The a is a constant, so this is 9 is 3 squared. So this is the square root of 3 squared minus x squared, which means we're going to make a sign substitution. The substitution here is x equals a times the sine of theta. So if a squared is 9, then a is 3. So we're going to sub x equals 3 sine theta. And just like with any other substitution, you need to calculate your differential dx. Dx here would be 3 cos theta d theta. And we talked about the kind of backwards nature of these substitutions the other day. You don't need to find anything floating around in here to match up or cancel with your dx. You're just going to plug in 3 cos theta d theta for dx. Don't forget to do this. For whatever reason, when it comes to trig sub, people forget the dx stuff. Don't do that. Always write your dx's. And remember, when you make a substitution, you need to account for the differential. The other thing that I'm going to put in my substitution box is a little triangle. A little right angle triangle that I'm going to cook up from SOHCAHTOA, which will allow me to go back and forth from theta stuff to x stuff, which I'll need to do at the end. So little right angle triangle, the angle down here, I'm going to label as theta. If x is 3 times the sine of theta, that's the same as saying sine of theta is x over 3. And remember, from SOHCAHTOA, sine is the opposite over the hypotenuse. So I can interpret sine theta equals x over 3 using SOHCAHTOA, where x is the opposite side length and 3 is the hypotenuse side length. So the opposite side to the angle theta there is this side, so I label that as x. The hypotenuse is the side opposite the right angle. And that leaves a side length down here that I need to solve for. By the Pythagorean theorem, a squared plus b squared equals c squared. So I solve for this missing side length. I solve for this. If this squared plus x squared equals 9, then this thing has to be the square root of 9 minus x squared. And something most folks tend to notice is that the missing side length from your triangle is pretty much always the thing that told you to make the substitution in the first place, that square root. There are some exceptions, but if the substitution came from a square root like that, then that square root is your missing side length. Okay. So just like with integration by parts or U sub, you get all the stuff you need for your substitution together, put it in a box, and then get to plugging in. So let's get to plugging in. So that integral is equal to the integral of, I've got the square root of 9 minus x squared, and x is 3 sine theta. So under my square root, I'll plug everything in real slow and gentle. We can see where it all comes from. I'll have the square root of 9 minus, and now instead of x squared, I have 3 sine of theta squared. Downstairs, I had an x squared. That's going to be 3 sine of theta all squared, again, because x is 3 sine theta. And then very important, we don't forget the differential. This dx at the end is 3 cos theta d theta. So that's the integral with the substitution plugged in. And although it might not look like it at this stage, this is an improvement. Things are getting better here. Any questions about where any of these pieces are coming from? So we look at this integral here, the integral we're given. And within that integral, I do see a gnarly square root. I see something that looks like it matches up with my Trig Sub Bible. It's the square root of 9 minus x squared. So that's like the square root of a squared minus x squared. A squared is 9, which means a is 3. And then according to my Trig Sub Bible, if I see this in my integral, I should substitute x equals a times the sine of theta. A here is 3, because 9 is 3 squared. So I'm going to substitute x equals 3 sine theta. I calculate the differential dx right away before I forget, just like normal, take derivatives. Dx is 3 cos theta d theta, because 3 cos theta is the derivative of 3 sine theta. Then I also draw a little triangle using SOHCAHTOA. So here I isolate the sine theta term by dividing both sides by 3. I get x over 3 equals sine theta. I just wrote it the other way here as sine theta equals x over 3. And I interpret that as an opposite over a hypotenuse. That's how I draw my triangle. I draw this triangle and I label the opposite side as x and the hypotenuse as 3. That leaves this missing side length, which I had to solve for. And I solved for that in my head, just using a squared plus b squared equals c squared. If this thing squared plus this thing squared is equal to 9, then this missing side length must be the square root of 9 minus x squared. And the trick there was that the missing side length is always going to be the square root that told you to substitute in the first place. And then the last thing I did is just plug everything in. So everywhere there was an x, I wrote parentheses, 3 sine theta. Here and here. Those were both squared in the original integral, so they're both squared here. And in place of dx, I wrote 3 cos theta d theta, because dx is 3 cos theta d theta as calculated from the substitution. Now we just simplify. The main thing is to simplify the square root. There are some constants that are going to float around. My advice regarding the constants is to wait until you've cleaned up the square root, then combine the constants, then pop them out. Under the square root, I'll have 9 minus 9 sine squared theta. Because 3 sine theta squared is 9 sine squared theta. Just square both pieces. Downstairs also 9 sine squared theta, and over here still 3 cos theta d theta. The magic is about to happen. The magic occurs when you apply the trig identity under the square root. Before I can apply that trig identity, I need to factor a 9. That's what's going to give me my 1 minus sine squared. So I'm going to, inside the square root, factor out a 9. This is 9 minus 9 sine squared theta. So when you factor out the 9, you get 1 minus sine squared theta. And check that if you were to distribute that 9, you would get the thing we had above. Downstairs, I still have 9 sine squared theta, and off to the side, I still have 3 cos theta d theta. One minus sine squared is cosine squared. So under my square root upstairs, I have the square root of 9 cos squared theta d theta. This is the magic step, because here is where you go from having some subtraction under your square root to not having any subtraction under your square root. Everything else stays the same. Because there is no longer any addition or subtraction under the square root, just multiplication, I am finally free to take the square root of the stuff inside. The square root of 9 is 3. The square root of cos squared theta is cos theta. Downstairs, I still have 9 sine squared theta. Oh, did I lose a 3 here? Sorry, this should be a 3 cos theta. And off to the side here, still 3 cos theta d theta. And we're almost done. 3 cos theta times 3 cos theta is 9 cos squared theta. So I have 9 cos squared theta divided by 9 sine squared theta d theta. The 9's cancel, and this is why I said don't pop constants out at the start. Wait until you've simplified things inside, then pop them out. And we're left with cos squared over sine squared, which is cotangent squared. So we'll stop here. This is this is kind of all the 7.3 stuff. This is all the new stuff. So figuring out the substitution, plugging in the substitution, and simplifying. From here, it's a 7.2 problem. We're not done yet. Obviously, I still need to do this integral, but we are done with the new stuff. So any questions up to here? So this piece right here came from this piece right here. The 9, that first 9 is just hanging out. Nothing new happened to him. The minus sign hanging out. Nothing happened to him. When you square 3 sine theta, that's 3 sine theta times 3 sine theta. That 3 times 3 becomes this 9. And the sine times sine becomes sine squared. So from, are we comfy up to here? All right. So the next step, I factor out this 9. This is 9 times 1 minus 9 times sine squared theta. So I'm factoring out that common factor of 9, and that's what gets me here. So here to here, I factored out the 9, but I did everything under the square root. Yeah. Like if you were to redistribute this 9, if you were to distribute this 9 over this subtraction, you'd have 9 times 1 minus 9 times sine squared theta, which is 9 minus 9 sine squared theta. So I'm just factoring the 9 to get here. Cool, cool, cool. No worries. I promise you. Everybody else wondering the same shit. All right, so we factor the 9. That gives me my 1 minus sine squared theta. Then I can call that cos squared theta by the identity, 1 minus sine squared equals cos squared. Then I can take the square root. From here, we're in good shape. The square root is gone, so it's just a trig integral now. We combine the 3 cos thetas and 3 cos theta into 9 cos squared theta, cancel the 9s, and then cos squared over sine squared is cotangent squared. So we've had some time to stare at this now. Can anybody tell me how to integrate cotangent squared? Yeah, Quinn's got it in chat. We rewrite it as cosecants. So cotangent squared, according to the third Pythagorean identity, is the same as cosecant squared minus 1. And then cosecant squared integrates to negative cotangent. The derivative of cotangent is negative cosecant squared. So this would be negative cotangent theta minus theta plus a constant. And that's all the calculus steps done. But there is still work to do. The same sort of thing, by the way, you would do if you got tangent squared. To integrate tangent squared, you write it as secant squared minus 1. Very, very similar. I know it's kind of jarring to go right to left, but if you'll forgive the abuse of conventions, I'll come over here so I don't have to waste all this paper. Because it also puts me right under my triangle, which is the tool we need to go back. So I'm going to write this down. We've got negative cotangent theta minus theta plus c. And there's 2 pieces there. Both of those pieces, since this is an indefinite integral, need to be rewritten as x stuff. Right now I've got theta stuff, which is all well and good, but the original problem was asking about x's, so I should give the answer in terms of x's, not thetas. The purpose of drawing the triangle is so that you can read off any trig function of theta in terms of the variable x. So cotangent of theta, using SOHCAHTOA, tangent is the opposite over the adjacent. So cotangent theta is the adjacent over the opposite, right? This angle in here is theta. So the cotangent of theta is the square root of 9 minus x squared over x. And the negative out front is this negative. And then I have still here my minus theta. Theta we get from the substitution here, right? If x is 3 sine theta, that means sine theta is x over 3. I can tuck this in here in another color. If sine of theta is equal to x over 3, then taking the inverse sine of both sides, I get theta is the inverse sine of x over 3, like so. So this theta piece here is inverse sine of x over 3, and then you have Your plus c still on that, ladies and gentlemen. It's your final answer. It's a little on the gnarly side, a little bit, just a little bit. But this would have been downright impossible before. So this is a really big step forwards. And again, the power of trig sub, the big idea is that we can't get rid of these square roots normally. There's no algebra trick that lets me get rid of that square root. But by introducing trig functions and using trig identities, we can get rid of the square root. Part where we have to add. I'm looking for that part you're describing. I'm just not quite seeing it. So the last place where we have a square root of 9 minus x squared is really in that first piece. Oh, I'm just using the triangle. I see what you're saying. I see what you're saying. So cotangent of theta is the adjacent over the hypotenuse, right? When you think of SOHCAHTOA, the TOA is tangent, opposite, adjacent. So the tangent of theta would be x over the square root of 9 minus x squared, which means cotangent of theta, which is the reciprocal of tangent, is the adjacent over the opposite, which is the square root of 9 minus x squared over x. So this piece came from the triangle, where I just read off what cotangent of theta is. Cotangent should be the adjacent over the opposite. By the definition of cotangent is the adjacent over the opposite. So that's why we made the triangle at the start. Bueno. So here, I'll annotate here, right? This is from the triangle. And then you can take some time to look at that triangle and see if you can piece together the bits. It comes from SOHCAHTOA and the triangle here. And I promise, if you spend a minute thinking about it, you will get it. Okay. I do want to attack that integral we looked at last time. So I feel like we're ready for that now. That one is also a sign substitution. It's similar. So let's do it. Last time I promised that we would be able to find an antiderivative for the square root of 1 minus x squared. The actual substitution here is a little bit simpler. If you look at your Trig Sub Bible, that table, this square root does look like one of the square roots there. It looks like the first one. And a here is 1, right? Because 1 squared is 1. So this would be a Trig Sub thing. We're going to let x be 1 sine theta, or just sine theta, which means dx is cosine of theta d theta. And while I'm in here, I'll go ahead and draw my triangle. If sine theta is x over 1, I'm thinking of this as the opposite over the hypotenuse, SOHCAHTOA. Then I can draw a little triangle, little right triangle here, where this angle is theta. This is a right angle. The opposite is x, and the hypotenuse is 1. And solving for the missing side of the triangle, I find that's the square root of 1 minus x squared. So if you're doing any indefinite integral with Trig Sub, there's 3 things you need to do. You need to find the substitution, calculate the differential, and draw the triangle. There will always be a missing side length from the triangle when you draw it, because you're just going to have like opposite over hypotenuse, or adjacent over hypotenuse, or opposite over adjacent. Solving for that missing piece of the triangle can be done using a squared plus b squared equals c squared, or I think what most people do is just realize that it's the square root from the integral. Either one is fine, as long as you can get to it and you understand where it's coming from. Having done those three things, you're ready to plug into your integral. The square root of 1 minus x squared is the square root of 1 minus sine squared theta. Dx is cos theta d theta. And that's it. Now our trig identity tells us that 1 minus sine squared is cos squared. So I have here the square root of cos squared theta times cos theta d theta. And the square root of cos squared is cos. So this is cos theta times cos theta d theta. And cosine theta times cosine theta is cos squared theta. So that's all the trig sub work done. And now we have to remember how to integrate cos squared, right? So all of these boil down to a 7.2 homework problem. Anybody remember how to integrate the cosine squared function? Yeah, I can remind you those things. How do I do this guy? How do I integrate cos squared theta d theta? Anytime we're dealing just with even powers of sine or cosine, requires half angle identities. The half angle identity for cos squared is 1/2 times 1 plus cosine of 2 theta. I can pop out the 1/2 and then do a micro u sub on the cosine of 2 theta to get 1/2 theta plus sine 2 theta over 2 as my antiderivative. All right, so now again, all the calculus steps are done. This 1/2 is a constant multiple. He just came along for the ride. The integral of 1 d theta is theta. Be careful about this. It's not x, right? I know it's easy to get baked into our brain, this idea that the integral of 1 is x, but you're integrating with respect to the new variable theta. Just another reason why it's so important to always write your differentials. Integral of 1 d theta is theta, and the integral of cos 2 theta is a micro u sub. It is sine 2 theta over 2. Remember, in our preliminaries, these micro u subs are one of the things we need to do quickly. Before I go back to x's, I want to pause for a moment. You guys are seeing this for the first time, so it's it's okay if it doesn't jump out at you as an issue right away. Does anybody see a challenge? I need to go back to the variable x because my original problem was in terms of the variable x. My answer also must be The theta piece, I'm going to handle the same way I handled in the last problem. I'm going to write that as the inverse sine of something, right? Here, I'll just take the inverse sine of both sides. But the sine of 2 theta piece presents a challenge. What is the challenge presented by the sine of 2 theta given this information here? Can we tell what the sine of 2 theta is? Yeah, it's in a DM, so I'll let people think for just a minute longer. The angle in my triangle here is not 2 theta, it's theta. So from this triangle, I can tell you what the sine of theta is, what the cosine of theta is, what the tangent or secant or cotangent or cosecant of theta are. But I cannot tell you what the sine of 2 theta is, because the angle in here is theta, not 2 theta. So before I can do anything with this, I need to apply the double angle identity for the sine function to rewrite this in terms of sine theta and cos theta. Sine of 2 theta is 2 sine of theta cos of theta. It's the nice one. It's like we always want to pretend like the sine of 2 theta is 2 sine of theta. You want to pretend like the 2 can pop out. It doesn't, right? Trig functions in general don't work that way, but this is the closest thing that, this is the one that comes closest to doing what you kind of want it to do. Now, of course, this is all still over 2. And then you have your plus c. What I'm using here is the fact that sine of 2 theta is 2 sine of theta cos of theta. This was another thing in our preliminaries. It's the double angle identity for sine. Now I can cancel the 2's. And I get 1/2 theta plus sine theta cos theta plus c. And now I can go back to my x's. Now I have everything that I need to go back to x's, because I can read off sine theta and cos theta from this triangle. I can find theta itself by taking the inverse sign here, right? If x is sine theta, then theta must be the inverse sine of x. Sine of theta is the opposite over the hypotenuse. That's just x. Cosine of theta is the adjacent over the hypotenuse. That's the square root of 1 minus x squared. And now you're done. And this is indeed a pretty complicated antiderivative. Right? I wouldn't expect any of us to just imagine that this is the antiderivative for the square root of 1 minus x squared, but it is. If you differentiate this, applying the inverse trig derivative here, the product, power, and chain rules here, you will get just the square root of 1 minus x squared after everything simplifies. This is about an exam difficulty problem, just to give you a feeling for that. Certainly I do. So if you're looking for, the question was, are there any links to videos? Yes, lots and lots. And that's true for every topic in this course. If you ever want to see more videos, more examples, come into the modules. Under review material, I've got lots of stuff. Under volumes, I've got lots of stuff. All the Patrick JMT things, These are always examples of him working problems, usually problems out of our textbook. We've got integration by parts, trig integrals, and if you come here, we've got some trig sub examples here. And then the Paul's online notes have other problems. If you follow this link, I know I only have one of them linked here, but he has several other videos and you'll see them in the playlist suggested at the right. Yeah, trig sub example 2. He probably has others. But I really like Patrick JMT. I think he does a good job of running through these problems in a way that makes them easy to understand. But there are links to many more videos in the modules. Other questions on this one? So the question is, do we have an integral and derivative sheet? Yes and no, right? So yes, if you look in the textbook, the best one is in section 7.5, right at the top here. These are all the integrals that you should know off the top of your head, right? All of these are things that if you encounter them, you should be able to write down the answer right away. The bottom two, the two with stars here, I don't expect you to know these off the top of your head, but everything else I do expect you to know off the top of your head. So that's the yes. The no is, will you have something like this available to you on the test? No, no, you got to know this stuff. So most of these are things that certainly everybody should know immediately without even thinking about it, right? Power rule, e to the x integrates to e to the x, 1 over x integrates to ln of x. Integral of sine is negative cosine, integral of secant squared is tangent, right? All of these are things that are pretty fundamental. Some of them are possible to forget, like the integral of tangent as the natural log of secant, or cotangent as the natural log of sine. Like, I get that it's easy to forget some of these, but this is Calc 2, and the first part of Calc 2 is all about developing your integration skills. So these are just like you need to know your basic derivatives to get through Calc 1. You need to know your basic integrals to get through Calc 2. What my wife did, so I'll tell you two stories, right? My wife and I think quite differently, but we love the same sort of things. And it's been really fascinating because we both had to learn a lot of mathematics to follow our career paths. The way I learned all this stuff was by sitting down with a physical copy of the textbook and solving problems. And every time I needed one of these things, I would write the formula down on the page and then apply it. And that worked for me, right? After solving like all the problems in the book that I could make myself solve, which was a lot of them, these sort of things became second nature. I don't have to think about them. They're just right there on the top of my brain because I've used them so many times. That doesn't work so well for my wife. What she did is made flashcards, right? Because there's so much going on in all the problems that singular part of like, here's this step where you need to remember this thing, would get lost in all the other steps. So for her, she made flashcards, and that worked really well. So like each one of these, a flashcard. All right, if you find yourself solving problems and they're not sticking, the individual little things you need to remember are not sticking, try the flashcard thing, or Quizlet on your phone. Some people having your phone nearby when you study is a real fucking bad idea. And if that's you, don't do this shit, make flashcards. But if that's not you, if having your phone nearby is not like, you know, death to your studying, there's an app called Quizlet where you can generate flashcards. There's probably already a Quizlet for these sort of things, and you could use that to study these as well. But this is the collection of integrals that I expect you to know off the top of your head without thinking about it, everything down to number 18. You will not have access to a sheet like this for the test. You need to know it ahead of time. All right. What next? How about a definite integral? All right, we haven't done much in the way of definite integrals with trig sub. So we did that. That was fun. The area of the ellipse is a little challenging to do right out of the gate. That's a good one, but it's not definite. That doesn't require trig sub. But that's pretty fucking gnarly. How about something less gnarly, but also definite? Hey, yeah, let's do number 9, the integral from 3 to 2 of 1 over x squared minus 1 raised to the 3/2. I'll write it down over here. Is it 3 to 2 or 2 to 3? 2 to 3. And that was a 3/2 power, was it? Yeah. All right. There was a request a minute ago to write down the triangle relationships for the trig functions. So let me just remind you. SOHCAHTOA stands for sine opposite hypotenuse. Ka stands for cosine adjacent hypotenuse, and TOA stands for tangent opposite adjacent. So if I label this angle in here as theta, and these as the adjacent, opposite, and hypotenuse, then sine of theta is O for the opposite over H for hypotenuse. I usually write op and hype, but either one is fine. Cos of theta is the adjacent over the hypotenuse, and tangent of theta is the opposite over the adjacent. And the other ones, cosecant, secant, cosecant, and cotangent, can be gotten as reciprocals of these. So the whole triangle thing, this is what's going on in the background there. The substitution I'm going to make, it might not jump out at you right away because you might not see the square root, but there is a square root here. The 3/2 power is secretly a square root. It's the square root cubed. And it could be thought of either way. In general, a to the m over n can be thought of as the nth root of a to the m, or the nth root of a all raised to the m. You can think of it either way. I'm thinking of it the second way because that's what's going to make life easier. I want to simplify the square root and then deal with the power of 3. So this is the algebra rule that we use to kind of see where the square root is in this problem. The square root is the 2 downstairs in the 3/2 power to which this whole quantity is being raised. All right, so that's really the square root of x squared minus 1 all cubed. And you could put the cube inside. It could be x squared minus 1 all cubed and all under a square root. But if you think about it like that, it's going to make things nastier. Deal with the square root first. Looking at this integral right here, my Trig Sub Bible says, oh, square root of x squared minus a squared. So that's a secant substitution. We're going to let x be a squared is 1, so a is 1. So we're going to let x be 1 times the secant of theta, which means that dx is going to be the secant of theta times the tangent of theta d theta. This is a definite integral, not an indefinite integral. So here, I'm actually not going to draw a triangle. Remember, anytime you make any substitution in a definite integral, you need to change the bounds. So my old lower bound is 2. My old upper bound is 3. And what we need to do is figure out the corresponding values for the variable theta. So when x is equal to 2, what is theta? When x is equal to 3, what is theta? Oh, just ran it. Okay. Let's do the lower bound first. And I'll do some side work for this, I think, on a separate sheet. When x is equal to 2, we have, from this substitution, 2 is equal to the secant of theta, which is the same as saying 1/2 is equal to the cosine of theta. Secant is 1 over cosine, right? They are reciprocals. So if 2 is secant theta, take reciprocals on both sides. The left-hand side becomes 1/2. The right-hand side is the reciprocal of secant, which is cosine. So theta will be the inverse cosine of 1/2. What is the inverse cosine of 1/2? What angle between 0 and pi has cosine of that angle equal to positive 1/2? I told you there'd be a lot of trig here. So I'm looking for an angle between 0 and pi, somewhere in here, where the cosine of that angle is positive 1/2, which is right here. So what I'm doing is trying to change the bounds for our integral because we're making a substitution, and the integral is a definite integral. Always, to change the bounds, you take your old bounds, which were 2 and 3, and you plug them into your substitution, right? Just like with U sub or Z sub, to find your new bounds, you plug the old bounds into the substitution. So if I take 2 and I plug it in for x right here, I get this equation, 2 equals secant of theta, right? Just plugging in 2 for x here. And my goal is to solve for theta. So that gets me to this. Now taking reciprocals on both sides, flipping both sides over, I'm able to rewrite that as 1/2 equals cosine theta, because cosine is the reciprocal of secant. The way you solve an equation like this is by thinking about the unit circle, or since you guys are allowed to use basic four-function calculators, basic whatever, TI-30X2S calculators, you can solve this by taking the inverse cosine of both sides. The angle here, where cosine is equal to 1/2, has terminal point 1/2 comma √3/2. That angle is pi over 3. So when x is equal to 2, theta is equal to pi over 3. If you need to practice this stuff, again, there's links in the modules. You come up to the review material, go to Trig Review, Paul's online notes. Go to inverse trig functions. Right down here are all these sorts of things, right? Like the inverse cosine of √3/2. How do you find it? Cosine inverse of negative √3/2, sine inverse of negative 1/2, all this stuff. Also, things like these, which are good to play with. So if you haven't talked about inverse trig functions in a while, which I know is possible, you need to come back and study this stuff, or it will bite you on the test. I promise there will be at least one use of inverse trig functions on your exam, probably 2 or 3. Right, so it's in the review material on the modules under the trig review here. Check it out if it's feeling foreign. What we're doing is we're just solving this trig equation, 2 equals secant theta, which we get by plugging in the old bound here, x equals 2. What we find is that theta is pi over 3. If you do the same thing with x equals 3, we're kind of out of luck. 3 equals secant theta. That's the same thing as saying 1/3 equals cos theta. So here theta would be the inverse cosine of 1/3. And that's not a nice number. That's not like pi over 3 or pi over 6 or 4 pi over 7 or anything like that. It's not a pleasant number. So you can write it as the inverse cosine of 1/3, or you could write it as the inverse secant of 3. I think I'll write inverse secant of 3 because it just takes up less space. So this is how you change your bounds when doing trig sub. And again, it is an important step, right? This is something that you are required to do on the test. And if you need to practice it, practice it. If you can come to office hours to talk about it, come to office hours to talk about it. If you can't come to regular office hours, send me a Canvas message. We'll arrange one that works for you, but don't just let this shit slide, please. All right, so my old bounds went from 2 to 3. My new bounds go from pi over 3 to the inverse secant of 3. Everything else in the integral is going to go the same way as the last couple of examples. The only difference here is that we had to change our bounds. So my new bounds, my theta bounds, go from pi over 3 to the inverse secant of 3. Downstairs, I have the square root of x squared minus 1 all cubed. So that's square root of x squared is secant squared minus 1 under the square root all cubed. Upstairs, I just had a 1 and a dx. Dx is secant theta, tangent theta, so I'll write those here. Theta. Downstairs, under the radical, I can apply my trig identity. Secant squared minus 1 is tangent squared. And I get the integral from pi over 3 to the inverse secant of 3, secant theta, tangent theta, upstairs still. Downstairs, I have the square root of tangent squared theta, all cubed. D theta chilling. Square root of tan squared is tangent. We're looking at the integral from pi over 3 up to the inverse secant of 3 of secant theta, tangent theta, divided by square root of tan squared is tangent. That whole thing is cubed. So I get tan cubed theta downstairs and d theta over here. I can cancel one of the tangents. And I'm left with secant of theta divided by tan squared theta d theta. And now I ask you, how do I integrate secant over tangent squared? Any suggestions? When in doubt, rewrite as sines and cosines. So that's integral from pi over 3 to the inverse secant of 3. Secant is 1 over cosine. Tangent squared is sine squared over cos squared. So let's start with this. I leave the top alone, flip and multiply the bottom. So I get integral from pi over 3 up to the inverse secant of 3, 1 over cos theta times cos squared theta over sine squared theta d theta. I can cancel one of the cosines. And we're left with cos theta over sine squared theta d theta, which can be done two ways. One option here is to make a little substitution. Z equals sine theta. dz would be cos theta d theta. And you'd integrate 1 over z squared, which is negative 1 over z. That would require changing your bounds a second time. It's a little bit of work. So my suggestion instead is to stay in trig land and rewrite this as cosecant theta times cotangent theta d theta. Either one is fine. But 1 over sine times cosine over sine. That's what we have there, right? This piece is 1 over sine theta times cos theta over sine theta, which is cosecant times cotangent. And that should be jumping out at you. What is the integral of cosecant cotangent? Very good. Negative cosecant. Negative cosecant of theta. And we have to evaluate from pi over 3 up to the inverse secant of 3. So we get negative cosecant of inverse secant of 3. And that can be simplified. I will show you how. Minus negative cosecant of pi over 3, which you should know from your unit circle. Cosecant is the reciprocal of sine. The sine of pi over 3 is root 3 over 2. So this is 2 over the square root of 3 from the unit circle. To figure out the cosecant of the inverse secant of 3, I'd like to draw your attention back to that module. If you look at the inverse trig section down towards the bottom, you have statements of this sort. You can also Google around like cosecant of secant. And you'll find shit. All right, inversing cosecant trig function evaluating, inversing the calculator. How do you blah 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 blah? right? So there's lots of things out there you can Google around. I will show you. Here. This is something that is supposed to be taught in trig classes, but I have a feeling that depending on who you took trig with, it's a little sus. So what we want is cosecant, I'm ignoring the negative for now, of the inverse secant of 3. And you get it by drawing a triangle. We call this piece theta. So what we're after here is the cosecant of theta, where theta is secant inverse of 3. This is the same thing as saying secant of theta is equal to 3. 3 is 3 over 1, and secant is the hypotenuse over the adjacent, right? Cosine is the adjacent over hypotenuse, so secant is hypotenuse over adjacent. You draw a triangle. That is a straight up trig problem. Hypotenuse, adjacent. Now we will solve for the missing side length. This side right here, we'll call it B. We know that 1 squared plus B squared equals 3 squared. A squared plus B squared equals C squared, which means that B is the square root of 3 squared minus 1 squared, or the square root of 8, right? The square root of 9 minus 1. So this side length right here is the square root of 8. Therefore, the secant, sorry, we want cosecant. The cosecant of theta, which is the thing we want, is the reciprocal of sine. Sine is the opposite over the hypotenuse. So this is the hypotenuse over the opposite. 3 over the square root of 8. So this fellow right here, cosecant of inverse secant of 3. There's a negative out front, so it's negative 3 over root 8. Minus minus here makes plus 2 over the square root of 3. And that is your final answer. So this is a bit of work. I'm not going to pretend like that's not the case. All of these steps after getting to this are technically trig and calc 1 things, but you need to be real good at trig and you need to be real good at calc 1, right? Resolving that to this integral, cosecant cotangent, it's just using the definition of secant, the definition of tangent. The integral of cosecant cotangent, calc 1 integral is negative cosecant. And then finally simplifying the cosecant of the inverse secant of 3 to the 3 over the square root of 8. That's a trig thing, but only if you had a good trig class and only if you actually remembered it is that useful. So you may need to remind yourself how to do this stuff. Right? If you do, again, come by office hours, send me an email, look through the modules in Canvas. I've got lots of stuff there for you. But if you're feeling like you need more help, please come talk to me. I'm happy to help. Yeah, so for the purposes of screen caps and whatnot, let me pull this down. Here is our whole procedure. And then I'll do the same thing with the next page. Okay. Here's the other stuff. All right. So that's Trig Sub. On its own, it's not that bad. But most of these problems will require you to remember a bunch of stuff from your trigonometry class that may be forgotten or was rusty or just never got all that comfortable with back in trig. Because sadly, trigonometry here at Santa Fe is not what it should be. If you're feeling challenged by this stuff again, please come ask for help, right? I'm here for you. I can't take this stuff out of the class. I can't take it off the test, but I can help you get ready for it, all right? And I'm more than willing to do that. So if you're feeling intimidated, please come see me, right? I can point you to specific resources that you can work with on your own, and I can work with you myself. I can point you to tutors that are especially helpful. Whatever it is that works for you, I promise I can help you. But we got to get there. We are out of time for the day, so I'm going to go ahead and end our meeting here. Please try to wrap up the 7.2 and 7.3 homework over the weekend. Do not let this one slide. Next Monday, we're going to talk about partial fractions, which is section 7.4 in the textbook. That is a challenging one. And then after that, we're going to be getting ready for exam 1, which again is probably 2 Mondays from now, not next Monday, but the following Monday. So the judgment day is coming. I want to get you ready for it. I want it to go well. So please do everything you can to prepare yourself. And if you feel like you need a little bit of extra help, please come see me. I am more than happy to help you with this stuff. For a quick reminder, of course, we do also have tutors on campus. You can access the tutoring online by following the links here in Canvas. So just click this link to get to the tutors. It'll take you through a few other pages you got to click through. Of course, you can also go physically to the library. There are tutors there that will help you in the Learning Commons at the library, or you can come see me in office hours. That's it from me for today, guys. If you want to chat, I'll be in an office hour from 1 to 2. Otherwise, I'll see you all on Monday when we're talking about partial fractions. Take care.